Hello everyone, I'm Siva Satyendra and I'll be presenting some results from our work on enabling the implementation of CrossLayer Reliability in heterogeneous embedded systems. I'm currently working as a postdoctoral researcher with the Chair for Processor Design at TU Dresden. I completed my PhD last year from the NUS Singapore. It was in the field of reliability in heterogeneous embedded systems. To provide the motivation for this work, we shall start with the question of why cross-layer reliability. In the simplest of terms, the answer would be because of rising physical fault rates. This is applicable to both transient and aging related faults. If we consider both of these together in the bathtub curve, we note that in addition to the increasing soft error rate during the normal lifetime of the the normal lifetime itself is reduced as well. In this scenario, the question arises as to how do we keep electronic systems useful in the face of such increasing fault rates. The simplest answer to that is to keep on doing what has worked so well for many years. We adopt a phenomenon-based approach where we devise methods to counter each fault mechanism in the hardware layer itself. This approach makes the design simpler as it maintains the abstraction in the development effort for each layer. However, given the rising fault rates, limiting fault mitigation to hardware or for that matter to any one specific layer may not be feasible, especially in case of resource-constrained systems. In contrast, the cross-layer reliability approach involves distributing fault mitigation across multiple layers. This approach lets us leverage the implicit logical masking across the layers. In addition, there's a scope for quality of service aware design, where the optimization efforts are targeted towards one or more application-specific reliability metric. Uh, Also, since we have more knobs to tune, we might end up with more design points to choose from. Okay, so we implement cross-layer reliability. So what's the problem? Uh, let's look at uh, let's look at task mapping without any consideration of hardware heterogeneity or reliability. In this case, the scheduling involves deciding which task to execute next, and in task binding, we try to determine the processing element that has to be used for executing the task. If we bring in processing element heterogeneity and cross-layer reliability, each task can now have multiple implementations. So the number of design decisions associated with each task is now much more. So one of the problems that we need to solve for implementing cross-layer reliability is the efficient design space exploration in the context of hardware heterogeneity of HMP socks, the fault mitigation methods at each layer, and also the number of tasks that might be much higher in case of complex applications. A quick survey of the state of the art with respect to implementing cross-layer reliability shows the focus on these six aspects. Among these, we observed major scope of improvement across these highlighted factors. The selected DFS mode usually determines the software susceptibility and the aging effect due to power dissipation. Similarly, the design space exploration methods that have been used for task mapping in the related works do not actually scale very well with increasing degrees of freedom. Also, the task level analysis usually uh, does not include the integrating the effects of imperfect fault mitigation and implicit masking across multiple layers. These two factors are essential in the sense that when you implement cross-layer reliability, you want to estimate the impact of the distribution of fault mitigation across these multiple layers. To summarize, we have basically proposed a design space exploration methodology that enables the joint exploration across all these factors. This can be used for an early stage exploration of system level design decisions for implementing cross-layer reliability in heterogeneous embedded systems. If we take a quick look at the system model used in this work, we have used directed acyclic graphs to represent the application. The framework supports multiple task level implementations in addition to cross-layer reliability. Uh, Similarly, for the architecture model, we assume a heterogeneous multiprocessor system on chip, similar to the Zinc processing platform that's available from Xilinx. With respect to the reliability model, we assume three types of redundancies: spatial, temporal, and information. For the hardware, system software, and the application software layer respectively. The quality of service metrics supported in the current implementation includes average mix span, estimating the error probability, the mean time to failure, and the energy consumption. Here we see a multi-objective evolutionary algorithms-based approach to implementing DBFS and reliability over task mapping. In the corresponding encoding for the genetic algorithm, each individual is basically an ordered sequence of the configuration for implementing each of the tasks. The configuration for each task includes the design decisions with respect to the processing element, the implementation, the DBFS mode, and the set of fault mitigation methods for each layer. Another approach to this DNS exploration problem splits the process into two stages. The task level DAC finds the Pareto implementations for each task based on the relevant optimization objectives. Then the system level DAC then basically finds the right Pareto implementation that has to be used for each of the tasks based on the system level optimization goals. A comparison of the encoding for the genetic algorithm shows much more design choices for each task in the earlier approach. Each of the two approaches has its own set of benefits. And in our proposed methodology, we kind of tried to take advantage of the benefits of both these methods. We use the results from the Pareto implementations based search as seeds to the full configuration search. Similarly, the task level DAC results are used to limit the choices that can be used for each task during the full configuration search. For the task level DSC, we have used absorbing Markov chain based modeling to integrate the effect of implicit masking and imperfect fault mitigation. Here we see the models used for estimating the average mix span. The transition probabilities between the states is basically based on the task execution times, the masking factors associated with each associated with the reliability methods for each layer, and the coverage of the detection methods that are being used. The estimation is based on the absorbing Markov chain analysis. We used a similar approach for estimating the functional reliability. Unlike the earlier case with the average max span, here we have two absorbing states for each set of processes. And the corresponding analysis basically lets us estimate the probability of error with a given CrossLayer reliability configuration. If we take a look at the experiment results for task level DAC, here we see the Pareto fronts with respect to average execution time and probability error for three different DBFS modes while considering various cross-layer reliability choices as well. Similarly, this figure shows the Pareto front considering different levels of implicit masking across the layers. Finally, here we see the rising number of Pareto front implementations with increasing number of automation objectives in all the tasks of surveillance detection. This shows the ability of the proposed method for a co-analysis across different degrees of freedom. If, with respect to the system level DSC, this figure shows the benefits of cross-layer automation in one random synthetic application. The Pareto front with respect to average mix span and error probability obtained with the cross-layer automation is much better than that compared with an other layer agnostic approach. The higher Pareto front volume is observed across applications of varying sizes, which basically shows that the joint analysis can yield much better results in the system level DSC. Here you take a look at the comparison of the proposed system level DSC method uh, compared to that of the full configuration search. Again, the Pareto front with respect to average mix span and application error probability is shown here, and we see a much better Pareto front in an application with 50 tasks. This improved hypervolume of Pareto fronts is observed across applications of different sizes. To summarize, cross-layer reliability presents a cost-effective alternative for countering the rising fault rates. In this work, we have proposed an early-stage exploration methodology for efficient implementation of this cross-layer reliability. Possible improvements to this framework include the integration of other aspects such as communication and storage constraints of the architecture. Finally, I would like to thank you for your attention. The links over here can be used for contacting and the implementations for the proposed methods.